Blindfolded tasks. Close your eyes for a second and notice how quickly your confidence drops. The moment vision disappears, your brain loses its most dominant input and has to change strategies. Instead of reacting to what it sees, it starts predicting what should happen next. When you remove your ability to see, the brain has to rely on other senses such as hearing, touch, and proprioception. That forces more active processing in motor planning regions and the cerebellum, which handles timing and scaling of movements. By practicing blindfolded tasks, you train your brain to use body awareness and spatial memory more effectively, which sharpens attention and improves how you respond when visual information is limited, like moving in the dark, improving balance, or honing skills in sports where you can't always rely on sight. A simple way to do this is to close your eyes and write your name, draw a basic shape, reach for an object you just touched, or perform an everyday task such as brushing your teeth or brushing your hair. Your movements will slow down, your attention will sharpen, and you'll notice details you normally ignore. Stroop Effect. Reading words is so automatic that your brain does it even when it gets in the way. The Stroop task works by turning that strength into a liability. When you see a word, language systems activate instantly. If the task requires you to ignore the word and focus on the ink color instead, your brain has to suppress a dominant response. This engages inhibitory control systems, particularly the anterior cingulate cortex, which monitors conflicting information, and the prefrontal cortex, which enforces the rule. To try it, pause the video here or otherwise, look for a Stroop test online. It's simply a list of words in different colors, and your job is to name the color of the ink, not the word, as fast as you can without making mistakes. Practicing this strengthens impulse control and focused attention, making it easier to stop automatic reactions and stay on task when distractions get in the way. Non-dominant hand tasks. Have you ever tried writing your name with the wrong hand and realized how hard you had to focus, like your brain suddenly had to slow down and pay attention? That's exactly the point. Your dominant hand runs on autopilot. Those movements are so routine that your brain doesn't give them a second thought. But the moment you switch hands, that automation disappears. This recruits more activity in your motor cortex and premotor regions of the brain and puts more demand on the corpus callosum, the area of the brain that controls communication between hemispheres. Because the movement is no longer automatic, your brain has to stay actively involved, which sharpens focus and stimulates neuroplasticity. Non-dominant hand tasks are so effective at changing the brain that they are often used in stroke rehabilitation and movement retraining. Write a short sentence, eat with your non-dominant hand, or make it a daily practice by using your other hand to do common tasks like unlocking your phone. You'll notice the effort instantly, which is proof that you're engaging your brain. Motor imagery. Before your body moves, your brain already knows what's about to happen. When you visualize a movement without moving, you're training that prediction system directly. This is called motor imagery, and it's not imagination, it's simulation. Brain imaging studies show that mentally rehearsing a movement activates the same areas as physically performing it, the primary motor cortex, premotor cortex, and cerebellum. So, while visualization is weaker than real movement, it shares much of the same circuitry. This is why athletes use it. Visualizing the movement primes the motor system, helping them react faster and execute the movement more precisely. It's also used in stroke rehabilitation and in surgical practice as well. It's easy to try. Just sit quietly with your eyes closed and visualize your actions before you actually proceed. Imagine the scene and the details, picture the timing, the rhythm, and see yourself execute the movement flawlessly, then immediately go perform the task. Visualization alone has limits. Movement alone relies on habit. But when you visualize first and move right after, your brain plans the action ahead of time and then checks that plan against reality. The result is less anxiety, less hesitation, and better accuracy on the first attempt. Active recall. Have you ever known something perfectly until someone asked you to explain it out loud? That moment of pressure reveals the difference between recognizing information and actually being able to retrieve it. Active recall works by forcing your brain to reconstruct information without cues. When you remove the source and try to pull the information out on demand, the brain has to rebuild the pathway instead of passively following it. That process engages the connection between your hippocampus and prefrontal cortex, making it easier to recall facts quickly and more reliably the next time you need them. Adding a time pressure during recall can also strengthen encoding, meaning the information stays in your memory for longer periods of time. To do this as an exercise, look at a short list of words, facts, or images for 10 to 15 seconds. Then remove them and recall as many as you can out loud in under a minute. The time pressure will make it harder, but that difficulty is what locks it in. This isn't about testing yourself to see if you remember. It's about forcing your brain to do the work of remembering, which makes your memory stronger and information more accessible the next time you need to pull it up. Mental rotation. Some problems feel harder, not because they're complex, but because your brain has to manipulate them in space. Mental rotation forces your brain to actively transform information instead of just recognizing it. When you mentally rotate an object, your parietal cortex activates, the same region involved in spatial intelligence and mathematical thinking. It's not just looking at the object, it's internally manipulating it, which increases demand on working memory and spatial awareness. To do this as an exercise, picture a simple object, like the letter R. Now mentally rotate it 90 degrees to the right, then flip it upside down and rotate it 90 degrees again. Can you tell if it's forward or backward or which direction it's pointing at all? You can also train mental rotation through activities like Tetris or solving a Rubik's Cube, which require constant manipulation of objects in space. Practicing this improves spatial reasoning and speeds up decisions that rely on spatial and visual information. This kind of thinking shows up anytime you're navigating, assembling something, reading diagrams, or trying to parallel park. Concentration grids. If your brain feels scattered, it's usually because attention is spread too thin. Concentration grids teach intense focus and how to tune everything else out. A concentration grid, or Schulte table, is just a grid of numbers in random order. Your job is to find them sequentially as fast as possible. First 0, then 1, then 2, and so on. It sounds simple, but it forces rapid eye movements and selective attention. Your brain has to scan the entire visual field, filter out distractions, and lock onto the right target repeatedly. It's used in pilot training, sports vision work, and neuropsychological assessments because it trains focus and also activates the posterior parietal cortex, which handles visuospatial processing. An added benefit is that focused attention during the task can reduce anxiety in the moment by distracting you from your emotions and giving your brain a chance to calm down. You can find concentration grids of all different sizes online, 5x5 grids, 6x7, or whatever you choose. Start a timer and find each number in order as fast as you can. Keep a log of how long it took you and see how quickly you improve over time. Hand coordination challenges. Making your hands do similar actions doesn't require much brain power, but the second they're forced to follow different rules, coordination turns into real cognitive work. This is called bimanual coordination, and it's heavily studied in motor control research. When both hands do the same thing, one hemisphere can handle most of it, but when they follow different patterns, both hemispheres have to activate simultaneously and communicate through the corpus callosum. That increases neural crosstalk and forces constant negotiation between the two sides of your brain. Although you may not notice it immediately, the effect is measurable, which is why these tasks are sometimes used in neurorehabilitation and coordination training programs. It's easy to try, but harder than it looks. Make a fist with both hands, put your thumb up on your left hand, and just your pinky out on your right. Now switch rapidly and simultaneously between the two, so your pinky is out on your left hand and your thumb is up on the right. It's awkward at first, but improves with practice, as your brain learns to coordinate competing signals, improve timing, dexterity, and control. Reverse sequencing. Counting forward is easy because your brain already knows what's coming next. Going backward breaks that shortcut and forces your brain to do real work. Forward sequences are automated. Your brain predicts the next number without effort. But when it comes to reverse, your brain has to retrieve each step manually, which increases demand on the prefrontal cortex and executive control systems, and strengthens working memory by forcing information to be held and reordered in real time. This is why reverse counting is used in cognitive testing, dementia screening, and executive function assessment. It's easy to understand, but cognitively demanding to perform. To do this, say the months in reverse order, spell words backwards, or starting at 100, count backward by sevens, saying each number out loud. You'll feel the effort immediately. It's not that you're bad at math, you're just forcing your brain to think. Dual in back task. It's simple to remember one thing, but when you have to hold two pieces of information at once, your working memory is truly tested. The dual in back is an exercise where you're monitoring two changing inputs at once, one visual and one auditory. You see a grid where a square lights up in different positions. and you hear a letter at the same time. Your job is to remember whether the current position and letter match the ones that appeared a number of sets earlier. Each new signal pushes older information out, so your brain has to constantly decide what to keep, what to discard, and what to compare. Tracking two streams of information simultaneously activates prefrontal regions of the brain and trains working memory. And plenty of studies suggest that cognitive improvements last months after training is complete. This task doesn't feel hard because it's unfamiliar. It feels hard because you're pushing the limits of how much information your working memory can handle at once. None of these exercises are complicated, but they all work for the same reason. They interrupt autopilot and force your brain to stay actively involved. You don't need to do all of them. Even one or two, done intentionally, improve your focus, strengthen memory, and make your thinking more efficient overall.